start with the Lorentz cone spacetime. If this M gamma is an n-dimensional complete Riemannian manifold, actually it is an Einstein metric and with negative constant, then the 1 plus n Lorentz cone space-time, this curly M and this gamma bar is a solution to a vacuum Einstein equation in 1 plus n dimension. And there are several remarks for this space-time. It has expanding geometry with volume growth Tn, and when n is 3, then gamma is the hyperbolic metric, and then the space-time is the Muon model. It was also known as the Kappa is -1 vacuum FRW model. And one can also pass into the quotient, so that's considered a closed spatial manifold. Talk about this Einstein equation, so we should know this gauge. In a space-time metric takes the general form of 1.1. N is the lapse and beta is the shift. Then we can define the unit normal to the space to the spatial manifold, this capital T, and we can define the second fundamental form. The CMC time coordinate corresponds to this constant trace of the second fundamental form, and this is the time function. And with spatial harmonic gauge, this is called CMC SH gauge. It was introduced by Andersson and Moncrief. And there's also this Gaussian time coordinate, means n is the constant 1, and with this 0 shift, this is also called the Gaussian normal gauge, and this is the gauge that I will talk about in this talk. Concerning this Lorentzian cone spacetime, there are some previous stability results. It was started by Andersson and Moncrief in almost 10 years ago. And suppose this M and gamma is a stable Einstein manifold. It is also a closed n-dimensional manifold with smooth moduli space, or it could be rigid and an isolated point. Then they prove this stability of the Lorentz cone metric, and their proof in their proof they use this CMC SH gauge, and their framework was used in several non-vacuum contexts, in particular in 1+3 dimensional case, like massive Einstein-Vlasov, or Einstein-Klein-Gordon, or Einstein-Charge-Vlasov. And myself, I was also doing this for Einstein-Klein-Gordon, and the main difference from the others is that I use this CMC with 0 shift, and the energy estimate is also valid for non-compact spatial manifold. And of course, the 1+3 dimension and the general dimension case could be very different. The main difference comes from that the modular space of a negative Einstein space is non-trivial in high-dimensional case. And for the non-compact case, there were some stability results for this hyperbolic metric. Yeah, there was for rich flow case, the stability of the hyperbolic space. The proof was actually relies on this lower bound of the Laplacian and some formulae type inequality. Actually, because this rich flow is parabolic type equation, so it's very different from the hyperbolic equation. And myself and Yuan, we proved the stability of this three-dimensional hyperbolic space for this Einstein flow. It could couple with massive or massless scalar field. And I would like to talk more about the decay mechanics in this works. In the work of Andersson and Moncrief, the decay of gravity actually depends on the lowest eigenvalue of the Einstein operator, namely the linearized of the trace free part trace Ricci. And in particular, when n is 3, the lower bound of the eigenvalue is 1 on the compact manifold, and this will give almost t-1 decay rate. And moreover, because of this method, so this analysis requires smooth modular space. And the other one is the work by myself for this 1+3 dimensional Einstein Klein Gordon. The decay mechanics actually comes from the expanding geometry of this new model. And this was reflected on the Bianchi equation. Let's see, this curly E and curly H are the electric and magnetic part of the space-time Weyl tensor. And then the Bianchi equation takes the form of 1.2a and 1.2b. There was this linear term on the left-hand side. There's two linear term, and they have positive sign, and this will give the decay rate almost t-1. And why does this two linear terms? How does this two linear term comes? It comes from the expanding geometry. So this framework was also used in my joint work with Yuan to prove the stability of open minimum. So motivated by the work of Andersson and Moncrief, so we are thinking about it's possible to have some stability result for if in the case of non-compact spatial manifold. And we intend to develop techniques that are independent of the lower bound for eigenvalues of Einstein operator or the theory of moduli space of Einstein metric, or even CMC variation, because this involves constructing CMC data. And we know that on all these topics, little is known in the non-compact case. And this seems possible because the decay mechanics and hence the energy estimate in my work on this 1+3 minimum model, it holds even when this spatial manifold is non-compact. But in this higher dimension case, how will this non-trivial modular space affect the analysis, this fact is reflected on the structure of Einstein equation, and which will further indicates no decay for the spatial Weyl tensor. And we will see this in the proof. Now let's come to the before the statement of the main results. I will introduce some basic notations. The Gaussian normal gauge takes the form of 2.1, and we can define the second fundamental form. If this spatial metric G tutor is the n-dimensional hyperbolic metric, then we have this trace equals to minus n over t. So because of this t-squared factor, we have to do some normalizations. For instance, after this rescaling, this rescale G, in the case of n-dimensional hyperbolic metric, is exactly gamma, no t-squared gamma. And K, the scale K is exactly minus gamma. And sigma is the trace-free part of the K, and eta is the perturb of the trace part. So if we perturb the space-time, then sigma and eta, they are small quantities. And let me first introduce the main result in three-dimensional case. Suppose this initial hypersurface is a smooth and complete remaining manifold with positive injective radius, and M is diffeomorphic to R3. And the rescale data is close to the hyperbolic metric in some Sobolev norm, in some Sobolev space. Then the Curry M and breadth G is a global solution. It is a global solution to this Einstein scale field system, and we have this decay rate for the Ricci parts, and it implies that the metric will flow back to the background metric gamma. But when it comes to the higher dimension case, the spatial Weyl tensor does not vanish, and we have to introduce a non-positive Weyl tensor condition. It says suppose this is M gamma is an n-dimensional remaining manifold with dimension greater or equal to 4, then the Weyl tensor, we call this Weyl tensor non-positive if for any 0-2 types symmetric tensor, after contraction with this Weyl tensor and integrate on the remaining manifold is negative. And if gamma is the hyperbolic metric, the Weyl tensor vanish, and this gives a trivial example for this non-positive Weyl tensor. And let me state the main results in higher dimension. Suppose gamma is an Einstein metric with negative Einstein constant -1, and its Weyl tensor is non-positive. Similarly, we have the initial hypersurface is complete and non-compact with positive injective radius, and the initial data is close to the standard background Einstein metric. in some sort of space. Yeah, maybe one should know this regularity. And then the vacuum Einstein equation have a global solution. And during this Einstein evolution, there is the asymptotic decay rate for this perturbation and the second fundamental form. We can see that, however, for this metric, the metric itself remains close to the background, and the wire tensor also remains close to the background wire tensor, but it does not decay. So it means like this decay estimate implies that the metric will flow to an Einstein metric, a final Einstein metric with this G infinity. But however, the perturbed wire tensor does not decay. It means that this G infinity is not necessarily the background metric, although it still lies in a small neighborhood of this gamma. And this non-decaying character of this wire tensor is the main obstruction for this metric flowing back to the original metric gamma. And suppose in a particular case of hyperbolic space, then the wire tensor, the background wire tensor vanish, and we still get the G infinity is not necessary gamma. And this coincides with a result of Graham and Lee, which says the hyperbolic space admits deformations which are Einstein of the same Einstein constant and are not isometric to gamma, but remains close to gamma. And this is also a consequence of the non-rigidity of the hyperbolic space in higher dimension. And we know this is different from a compact case, because in this compact case, the hyperbolic metric is rigid. And there are also several remarks. And we can see in the proof the proof is also valid when the manifold, the spatial manifold is closed. So what does this non-positive wire tensor condition means if in the compact case implied by a Bochner formula, this non-positive wire tensor condition indicates the Einstein operator has a positive, the eigenvalue of this Einstein operator must be positive. It means that now in the compact case, this gamma is strictly stable and rigid. Yeah, and now let me come to the parts of the proof. And so let me show you the Einstein equation in this Gaussian normal gauge. In particular, if we have this two transport equation and the Gauss-Kodash equation, and we have this because now it's not CMC, so we have this trace part. But in terms of the perturbed variables, this transport equation takes the form of 3.3, and we can find that because of the expanding geometry, we have also this positive linear terms on the left-hand side of the transport equation for sigma and eta. And these two terms will give the almost t minus 1 decay rates for eta and sigma. And we also have this constraint equation. And so first of all, we have to think about this Gaussian normal gauge. The local theorem, actually it was proved very early by Andersson and Randall in the category of analytic, in the analytic category. And more recent, it was proved by Rook and his collaborator for this bounded energy data. And we know this Gaussian normal gauge will give an Riccardi type ODE for this trace of second fundamental form. So this will need to blow up in the asymptotic Frege case, but in the actually we are close to the asymptotic hyperbolic case. There's no blow up for this gauge because the trace K is initially negative. And there's another benefit for this gauge because it allows non-CMC data straightforward. Otherwise, why one should, for example, if we are in the CMC gauge, we should remove this CMC restriction on data by finding the CMC surface in the local development for data close to CMC, and this is a different story. And I will give you, I will talk about some main idea in the lower dimensional case. First of all, because this Gaussian normal gauge is non-borderline terms for Klein-Gordon field, so it offers a significant simplification for proof of the previous work, and secondly, there is a structure of saving regularity for this eta x 3.3b. So we can see this, we can compare these two equations. On the right-hand side of 3.3b, there's eta and sigma. In a vacuum case, the space-time reach vanish. And this eta and sigma, they are the first derivative of metric, right? But like for 3.3c, this equation involves this curly E. Curly E is the space-time Weyl tensor, some component. So it involves two derivatives of metric. So it means, so we can see actually the first equation has the structure of saving regularity. So that's we can prove we can a priori estimate the lower order of this eta without losing regularity. And after that we can move this eta part to the left hand, to the right side. Then the Codazzi equation now becomes an elliptic system for the sigma, and then we can do elliptic estimate for this trace-free part of the second fundamental form. And finally, there's a decoupling in the energy estimate because of working with this Bianchi equation coupled with the equation for the second fundamental form. the energy estimate can be closed without referring to the top order of eta. And so this decoupling structure help us to close the energy estimate, because the top order of eta actually does not decay because of this Klingon source. So in summary, the method in this n equals to 3 is independent of this same separation and independent of the theory of this moduli. It does not need any information of this moduli space, and even some analysis for eigenvalue of the Laplacian or Einstein operator or some Poincare type inequality. Instead, it requires observation for a structure of Einstein equation. Now, in the higher dimension case, because of this non-trivial modular space, there involves more interaction between different components of the Weyl tensor and more interaction between the Bianchi equation and the other geometric structure equation. And now we will see. And let me give you some notations. This H is the projection of tensor onto the spatial manifold. And we do this when present splitting for the space-time. This is the space-time Weyl tensor, the scared one. The curry E and curry H, they are like the electric and magnetic part. And this curry K is the projection on the spatial manifold. Of course, this K is not necessarily a Weyl tensor on this spatial manifold. So we take the Weyl path. It was defined by this curly J. So and these variables, they have good properties, like curly E is symmetric and trace-free, and this curly H is symmetric in the first two indices and trace-free and satisfies the algebraic identity, and curly J is a Weyl tensor. So if the dimension is lower, like n is less or equals to 3, then curly J vanish. And so implied by this Gauss-Kudai equation, this curly H is supposed to bound the second fundamental form, this sigma, and the curly E is supposed to bound the rich part of the spatial manifold, while this curly J is related to the Weyl tensor of the spatial manifold. So if we have estimate for this three quantity, we then have the full information of the geometry. And the next, we'll do the estimate for this three quantity. Yeah, the main equation involves this transport equation for this eta, and the Bianchi equation, actually it is two transport system for this three quantity, and also involves an elliptic system for this curly J. And here is the two transport system, and we can see that So implied by this expanding geometry, there's this on the left-hand side, there's this linear term with positive sign, and they will give this structure which determines the decay rate of all these variables. Actually, in this n, if n is 3, the system, this system is essentially the Maxwell type equation. But in the general dimensional case, the principal part of this system takes the following form. This is essentially equivalent to a first order hyperbolic system. This was proved by the work of myself and Liu Cao and Todd for Einstein-Xiamen system. And so that's so. And for the proof, we will have to do the energy estimate for this couple of system. We begin with the bootstrap assumption, and so in this bootstrap assumption, we can see that the sigma and the second fundamental form and this curly E and curly H, the decay rate is almost T-1, and but this spatial Weyl tensor, it does not decay, and this is determined by the Bianchi equation, and we will see that. First, we have this transport system for this curly H and curly J. So, but the fact is, in this transport equation for the curly J, there's no this linear term with positive sign, and so the result is this curly J does not decay from this system. Yes, so this system tells us that the Weyl tensor, the spatial Weyl tensor, does not decay. And for example, we do estimate for this system. We just multiply this curly H and curly J on this equations and integration by parts. We got this L2 bound without any difficulty because we know from this bootstrap assumption all of the other quantity decays better than this curly J, and this J0 is the initial part of, and this quantity is small. So, but this bad news is the transport system does not decay for this Weyl tensor. But the good news is there is an elliptic system for this J, which comes from the Bianchi identity, the spatial part of the Bianchi identity, and this Bianchi identity implies a Laplacian equation for the curly J. So we have this elliptic estimate for the curly J. So it means that this we can bound this high order estimate by the L2 itself, and the L2 itself is already bounded in the first step. And so this elliptic estimate has a linearization mechanics. It means the higher order estimate for this Weyl tensor actually reduced to the L2 itself, and this will be useful in the following estimate. Now here comes the main system is the hyperbolic system for the curry E and curry H. And of course, these two systems, they are not independent. We will find that in this system, there's positive sign linear term. And so this is good. That gives the decay for this curry E and curry H. But we see this red term on the right hand side. This term will be startled because now the Weyl tensor fails to decay. But in the 1+3 dimensional case, the Weyl tensor vanished. So this is the additional difficulty in high dimension. So to handle this term, we in this energy estimate we just multiply this curry E and curry H and increase integration by parts. So this subtle term is here, and now we have to use the geometric structure equation, the transport equation for the trace-free part of the second Feynman form to replace this curry E by this equation, and we find that this term becomes a divergence form and plus some lower order term. So in order to make this energy estimate successful, so we in here is the place we will introduce the non-positive condition for Weyl tensor, so that the boundary term gives the positive term in the energy identity. So this is the zero order energy estimate. And for higher order energy estimate, we need more dedicated computations. This computation is actually the higher order version of this part. Yeah, the higher order version, and we can see in this identity there is this is a quadratic term. Now let's forget about the cubic term for a moment and focus on this quadratic term. And so if we just estimate this quadratic term directly, there is some loss in the decay. And the idea is this divergence curry H, we use the transport equation. See, there's this divergence curry H to substitute into this formula, and we will say this quadratic terms is equal to a divergence part and a term with positive sign. This is a favorable sign, and so that we have the higher order energy estimate in energy inequality in this this sign is good, so that's we got some additional energy term, and because the good sign of this the R term, we got some additional Bach integral. And for a higher order energy estimate, so I will not go to the details, but the main idea is we can use the inductive proof, because now we should remember, because of the elliptic estimate for this bad spatial non-decaying spatial Weyl tensor, it has a linearization mechanics, and this helps to close this inductive proof. And second, we have this positive Bach term on the left-hand side, and this will also helps in the higher order energy estimate. And finally, there's also some related problem. I think the most relevant one is if one can consider this kind of stability result in some weighted Sobolev space to give more control on the behavior of solutions at infinity. And because of the constraint equations, when the weight should not be too strong, this is the most difficult part. So thank you for your attention. And
So let's thank Professor Wang for the wonderful talk.
yeah.
So if we have any questions from the audience, yes, please unmute yourself and go ahead and ask questions.
Yeah. Should I just stop this share screen?
You can keep the screen up, like if somebody want to ask questions, you know. Yeah.
Yeah. It's more convenient. Yeah, let me go to this main theorem.
Was there a question from the audience? Like, if there is, please unmute yourself and, like, you know, feel free to ask. Oh, okay, so there is no question from the audience. So if there are no, yeah, I, I guess it is. The talk was actually pretty clear. So I guess I'll ask, you know, I guess I'll ask a couple of questions.
Yes, thank you.
Yeah. So can I ask a couple of questions? I guess.
Yeah, please. And thank you. Please.
Yeah. So yeah. So you mentioned this the Weyl, the special part of the Weyl curvature actually don't decay, right?
Yes.
What is there, like, you know, do you actually have to like go through all the structure of the Einstein equation to, like, is there like a kind of a reason behind that, like why that is happening, or like you actually, or is it just the structure of the Einstein equation as it is?
I think it is the expanding geometry, the rescaling, the rescaling is itself. The rescaling. Where's the rescaling? Yeah. I think it is this expanding geometry, and the rescaling itself determines this linear term.
Right.
Yeah, determines all of the equation, the Bianchi equations. I think it seems there's nothing to do with some other geometry structure. Is, of course, we have to impose some conditions like non-positive Weyl tensor to prove the stability, but this but actually I think this non-decaying structure comes from this expanding geometry.
Right. So you kind of once you scale that things out, that
So
becomes
you automatically got this.
right. So okay, and in the condition that you have, this that's some non-positivity condition on the Weyl curvature.
Yes.
Yeah, is that a generic condition, or like or is that just like an assumption, or like some space-time to satisfy that?
Actually, I didn't find any example, only this trivial example, the hyperbolic metric.
Right.
Yeah, because this is an integral condition.
Right.
Integral conditions. It seems hard to find this, but I think there were for people doing this Einstein metric, they were also imposing conditions, similar conditions for like Riemannian tensors.
I see. I
Yeah.
see.
So yeah.
Okay. Thank you. Yeah, that actually clarifies. Yeah.
Yeah.
Thank you. That
So
was a very nice talk.
yeah,
So,
we can.
do we actually have any more questions from the audience?
Um, where's the tune?
Yeah,
Hi.
Zoo, do you have
Hi.
questions? Yeah, go ahead.
Yeah.
but maybe I have a stupid question.
Hi.
You have to consider the elliptic equation, right?
Yeah. Elliptic equation
Uh,
of
do you
this.
have to consider the boundary affection?
Oh, the boundary.
Yeah.
They all vanish because of this Sobolev in
You mean you have make they will approach to
because
trivial
because
trivial
of the
data.
density theorem for this Sobolev space, and
Okay.
yeah, so there's nothing in infinity, but
Okay.
yeah, we know
So
that
don't have to consider the boundary.
we
Yeah.
know that they are zero at infinity, but we do not know their actually decay rate in terms of this in terms of this spatial geodesic distance. So this is why I think it would be worthwhile to consider this weighted Sobolev space-time.
Okay. Okay.
Yeah, space. And
Okay.
so in some weighted Sobolev space, it's possible to control the behavior. of the solution at infinity in more details.
Yeah. Okay, thank you.
You're welcome.
All right. So if there are no more questions, let's thank Professor Wang again for this wonderful talk.
Yeah.
And we will see everybody next week.
Yeah. Okay.